Section 4.1 Extrema on an interval. Objective. In this section, we're going to define what is extrema of a function on an interval and define relative extrema of a function on an open interval and closed interval.
First thing, let f be a function with domain D, then f has an absolute maximum value on that domain at point C if the value of the function at C is always greater or equal to, compared to all other values of that function in that domain. That's called absolute maximum value, which is also called largest value of that function. Absolute minimum means it's the smallest value of that function in that domain. So the value at C is called absolute minimum if this value is always less or equal to all the values in that domain. So look at the some possibility here for the first graph. As you can see that this is the graph of parabola on the domain is from negative infinity to positive infinity. As you go from left to right, the minimum value of that function exists, which is at 0. So 0 is the minimum value, which is also called absolute minimum, or the smallest value of the function at 0. And there is no absolute maximum value because the value, the graph is keep going up. So for the first one, there is absolute minimum here, but no absolute maximum. For the second one, we are just restricting our domain from instead of starting from negative infinity to positive infinity, we're just focusing on 0 to 2. So this is the first point and this is the last point. And as you can see that this is this absolute minimum value and this is the absolute maximum value for this function on this domain. This one, again, we're focusing on interval 0, 2 where 0 is not included. So because 0 is not included, that is open circle. And then the value goes up to 0.2, which is the value 4. At 2, the value of the function is 4. So as you can see that this graph has absolute maximum value at 2 and the value itself is 4. But for the minimum value, there is an open circle, and what comes right after that, we don't know about that thing. That's why the absolute maximum only possible for this one, and there is no absolute minimum. The last one, if we take the value of the very same function on the open interval from 0 to 2, there is no absolute maximum and no absolute minimum, because as we focus on this graph, you can see that the absolute maximum should be right before the value of the function at 2, but we don't know what comes right before the value of the function at 2, because so there is no maximum or no minimum. So based on where you are focusing, how you are defining your function on which domain, you might have absolute value, absolute maximum value or absolute minimum value, or sometimes just one of them is possible. The extreme value theorem, there is one theorem. It says if f is continuous on closed interval, so remember this is the this is the thing you have to focus on, closed interval. If a function is defined which is continuous function on closed interval, then f attains both an absolute maximum value, let's say that is capital M, and an absolute minimum value, let's say that is small m, and then the rest of the value of that function would be in between that maximum or minimum value. So what this theorem says, this theorem, where is that, that extreme value theorem, if we have continuous function, so function, that function has to be continuous, and number two, it has to define on a closed interval. If that is the case, then we always have absolute maximum or absolute minimum value of that function possible. So let's see some of the examples here. So the first one, if you see here the graph, in this graph, as you can see that the function is defined from point A to point B. This is the domain from A to B, and then this point, this value capital M, is the maximum value, which is the absolute maximum value of this function, and this small m is the absolute minimum value of the function, and both of them are inside the domain, and so at interior points. If you go to the second example here, your maximum and minimum value, this is the maximum value and this is the minimum value. I'm talking about the absolute maximum or absolute minimum, and they are at at endpoints. Here, the third one, the absolute minimum is at left endpoint, but the absolute maximum is at in a, an interior points. Okay, and fourth one, the absolute minimum is at interior points, and then absolute maximum is at the right endpoint. So we might have different kind of situation based on different kind of if your function is continuous and that is defined on a closed interval. Always we should be able to find out the absolute minimum and absolute maximum value of the function, but we might have different situation like this. So let's see one more example here. This function is defined from 0 to 1, but the value of the function at 1 is 0 itself. So this function is actually not continuous because you see the break here. If you see there is a break, then that is not continuous. So this function does not have absolute maximum value because it does not satisfy the condition of the extreme value theorem. Okay, the extreme value theorem. So to have absolute value, absolute maximum or minimum value both available for the function should be continuous function and it should be defined on closed interval. But here this function is not continuous function. Let's look at one example. Sketch the graph of the following function. The function is given, which is y equals 6 times sine x, and the domain is given, which is open interval. So first of all, to analyze this graph or to talk about this problem, we should know the graph of sine x function, sine function. So the graph of sine function is, if you start from 0 and go up to 2 pi, the graph of sine x looks like this. At 0 it's a 0, at pi over 2 it's a 1, at pi it's a 0, at 3 pi over 2 it's a -1, -1, at 2 pi it's 0. So this is the graph of sine x. Here we're looking for the graph of 6 times sine x. So whatever value of y you see here, you just have to multiply that by 6. But one more thing, here the domain does not include 0 and 2 pi, so we cannot include this endpoints. So there should be open circle here. So rest of the value you just multiply the y coordinate by 6. So for example, at pi over 2, the value should be, instead of 1, it should be 6 because you are multiplying the sine x by 6. At pi, 0 times 6 is 0. At 3 pi over 2, instead of -1, the value should be -6. So this is the graph of sine x on 0 to 2 pi, not including 0 and 2 pi. Now these are the options we have available for the graph of y equals 6 sine x, and we already know that at endpoints 0 and 2 pi the value would be there is no value, so there should be a hole. So find out the graph which has hole at 0 and 2 pi. So these are the two graphs which you see, where you see the hole at 0 and 2 pi, but the nature of the graph should be look like this. So first goes up and then so as you can see that this is the right graph. Okay, now determine whether the function has any absolute extreme values on its domain. So look at the graph. This is the right answer, and as you can see that this is the extreme maximum, which is absolute maximum, and this is the absolute minimum value. So that is possible. So one of the option we have to choose where both absolute maximum and minimum are possible. The function has an absolute maximum at x equal, which is pi over 2, and then function has the absolute minimum at x equal 3 pi over 2. And one more time, there is another question. Explain the results in terms of extreme value theorem. So if you go back to the extreme value theorem, it says that if function is continuous on the closed interval, then there should be extreme maximum, absolute maximum and absolute minimum possible on that interval. But here we took the open interval, but still there is an absolute maximum and absolute minimum. So let's read the options we have given here. Since the function is not continuous, but that's not true statement because this function is continuous. There is no gapping, there is no jump. So that statement is not true. Let's go to the next one. Since the function f is continuous on closed interval, uh, but that is not closed interval, that's open interval. So let's go to the next step, next option. Since the function is continuous on an open interval, it may or may not have the absolute extreme values on its domain. This is the statement we can generalize from extreme value theorem, but for this particular problem, we do have extreme maximum and extreme minimum value. But this is the only suitable statement we can pick from this four. Okay. Okay, so sometimes instead of getting absolute maximum or absolute minimum, we might have local maximum or local minimum. Local means instead of focusing on whole interval, whole domain. For example, let's say this is the domain of the function. The absolute maximum means the largest value of the function on this domain. Absolute minimum means the smallest value of the function on this domain. Local maximum means, let's say for example, this is the graph. You see, this is the graph, for example. Then as you can see that this point, the value of the function at this point is greater than the value comes before and comes after. That is called local maximum. The value of the function at this point here is smallest compared to the value just before that and just after that. That's why it's called local minimum. So this kind of values are called local max or local min. Okay, a function f has a local maximum value at c within its domain D if the value of the function at that point c is greater or equal to f of x for all x in D lying in some open interval containing c. So what they are saying is this D, we are just focusing on some small interval inside this whole big D. Instead of focusing on from a to b, we're just focusing on a small interval nearby that point. So always compare the value of the function just before and after, and then if it's greater, then that's called local maximum. If it's less, that's called, if it's smaller, then that's called local minimum. Okay, so here's the one graph here. As you can see that this is the graph of a function. This is our absolute maximum value and this is our absolute minimum value because that's the largest value on this domain and this is the smallest value on this domain. But this point is called local maximum because the value of the function at this point here is greater than the previous value of the function, and then after whatever comes after that point, the value of the function just right after that value. So that's why it's a local maximum. This is local minimum and this is local minimum because there is nothing comes right after that, so you don't have to compare if that is not inside the domain. But this is smaller than the value just come before that, that value. So there is a one test called the first derivative test for finding the local maximum or local minimum value. The first derivative theorem for local extreme values. If f has a local maximum or minimum value at an interior point c of its domain, and if f prime is defined at c, then the derivative of the function at that point would be 0. So remember, to have a local maximum or local minimum, always the graph at that point look like this. Okay, this is local maximum and this is local minimum, and at that point if you try to draw a tangent line, that tangent line would be always a horizontal line. That's why the derivative of that function at that point is 0 because that's the slope of the tangent line at that point. So there is a one definition, and that's a very very important definition, that's called critical point. An interior point of the domain of a function f where the derivative of the function is 0 or sometimes it's undefined is called critical point. So you have given a function f of x, you find the derivative of the function, and there are two different situations you might have. One is the derivative of function is 0 or the derivative of function is undefined at those points. In both situations, those points are called critical points. Either it happens the first one or the derivative does not exist at that point. Those kind of points are called critical point. And these points are very important for finding the extreme value. Extreme value means largest value and then smallest value, and that comes from this rule: finding the absolute extrema of a continuous function f on a finite closed interval. So there is a function f of x that's defined on closed interval a to b, for example, and this function is continuous function. Then to find out the absolute maximum value or absolute minimum value, what we need to do is we need to first find out all critical points. So we can find out the all critical points by finding the derivative of that function, and if and equate with 0. By solving that equation, it will help us to find the critical points. And sometime maybe the derivative doesn't exist, that also tell us the critical points. So first of all, if you have given a function, continuous function, on the closed interval, find out the critical points, find out the value of the function at those critical points, find out the value of the function at endpoints, and compare them. Wherever the largest value among them would be the absolute maximum value of the function on that interval, and the smallest value would be the absolute minimum value of the function at that interval. I'm going to show you one example here, but before that, sometimes you might have situation like this graph doesn't have absolute maximum or absolute minimum, though this is continuous function, but we are not focusing, we are not making it on closed interval. Okay, it's not on the closed interval. The same goes here. There is no absolute maximum or absolute minimum, because the domain is not closed. The domain is everything from negative infinity to positive infinity. So let's look at one example here. Determine all critical points for the function. Remember, to find the critical points, you need to find the derivative of the function if it exists. If it does not exist, then that means that point is the critical point. If it exists, then equate that derivative with 0 and solve for x. So in this case, if we find the derivative by using the power rule, it would be 12x minus 6x squared. Now we equate this derivative with 0, which is which gives us quadratic equation. Now we need to solve by factoring the greatest common factor here, and that will be it will give us two different options: 6x equals 0 or 2 minus x equals 0. If we solve for x equal to 0 and x equal to 2, so these are the 2 points where the derivative of this function is 0. So these 2 points are called critical points. Okay, remember, critical points means an interior point of the domain of the function f, where f prime is a 0 or undefined, is a critical point of that function. So in this case, we found the 2 points, x equal to 0 and x equal to 2, where the derivative of the function is 0. That's why these 2 points are critical points. So now by using the critical points, we can find out the extreme maximum or extreme minimum value of function like this. So here, first of all, you have given a function, find out the critical points. So that means find out the derivative of this function, which is 2x, and then equate this derivative with 0. So that means 2x equals 0. Solve for x, and that will give you the critical points. Critical point, you might have 1 point or more than one. Now if you try to find out the absolute extreme value, that means you have to follow these 3 steps. The first one, find all the critical points, evaluate the value of the function at those critical points and endpoints. So there is just only one critical point, so we need to evaluate the value of the function at 0, which is basically 0 minus 16, because x is 0, so that is basically negative 16. And now find out the value of the function at endpoint. Here you can see that endpoint is negative 5 and then positive 4. So plug x equal to negative 5 here, which is 25 minus 16, because negative 5 square means 25, which is 9, and this is 4 square minus 16, which is 0. So now we just have to compare 3 of them. So wherever you see the largest value, that is the absolute maximum value, so which is this one. Wherever you see the smallest value, that is the absolute minimum value. So the absolute maximum value is 9, and then absolute minimum value is negative 16. and you get the absolute maximum value at -5, and you get the absolute minimum value at 0. Okay, then the graph of the function, this is just as you can see that this is the graph of the parabola and shifting 16 units down. So this would be like this, but we have to focus from -5 to +4. So -5 is here, +4 is here, and at 0 this is -16. So this is the value at -5, that would be +9. So this is the graph. Okay, and I plot the graph by using the graph of parabola x squared and shifting it 16 unit down from -5 to +4. We just have to focus from here to here. Okay,